Go. Okay, that was Silent Night. As soon as I get my stand situated here. Okay, this is in the bleak midwinter. Let's see. Sorry, I gotta get this straightened out. Okay. Let's see. In the Bleak Midwinter was originally written by Gustav Holst and arranged by Kathy Peck in this arrangement. And then a flourish at the end. I go with Tammy.
Thank you so much, Kim. That was just wonderful. We really appreciate it.
Oh,
Great
thank
way
you
to
so
start the
much.
evening.
Oh, thank you. I hope everyone has a very nice new year.
Oh, I think we're about ready to get the meeting started. Um, Everybody, can you hear me? Okay. Um, Welcome everybody to the January 2026 meeting of Orange County Astronomers, the first meeting of 2026. This also is our the last day of our election, and don't make it too reverberant. Well, when we checked earlier, people could. Anyway, um, for those of you who may not have voted, but are members in good standing and want to vote, we have some ballots down here, thanks to Charlie, and some envelopes, and the instructions on how to cast your vote is on the ballot. So please feel free to come down and take advantage of them. The actual, if you don't vote here and you haven't voted electronically, and for some reason you can't vote electronically, if you get your ballot in so that it would be postmarked by midnight, it can still be counted. You know, just a hint. Anyway, with that, I guess I should, as usual, introduce myself. I am Barbara Toy. I am the current president of this wonderful club. And unfortunately, we are operating tonight without Raisa, who is unavailable. So there may be some rough patches because Raisa does an excellent job of coordinating these things, but we are going to go through as well as we can. And I'd like to thank Alan Smallbone, who has stepped in as the substitute host to take care of the Google aspects of it and help keep us on track. Okay, before we get started with the main business of the meeting, I believe that Doug Millar had worked out a this isn't really a raffle, but it's something to do with library books. So would you care to explain?
Right. Good. Hi again. This is a way to get people to the meeting earlier. No, I mean, this is a way to get rid of some of the library books. And do you remember that? I think sometime in October we did this, and I have OCA's answer to Vanna White. And what's your name?
I'm Laura.
So we have Laura here. She's going to do the actual auctioning. So the idea is you choose a number between 1 and 20, not 1 or 20. And if you win, you get this bag of books. Laura, tell us what's in the bag of books.
Well, this has 4 books. I should have looked. We've got atlases.
Nearby Galaxy Atlas with pictures and charts.
I see I have to.
It's a cloudy night.
It's a cloudy night.
Laura's a new member, by the way. So this is the first bag.
If anyone is interested in a bag with 4 atlases inside, then please think of a number between 0 and 20. It's not 0, it's not 20. I'm gonna whisper the number to Doug so that he knows that we're not cheating, and then raise your hand if you want this bag of books. Oh. Okay.
What's your guess? No.
Oh, someone doesn't want the bag of books. All right. Here. Thank you. Right. So, what was your guess? 12? Okay. What was your guess? 15? 8? Also 8? 11? 13? And one last person? Sorry, what was that? 7. I think our closest was 5. Oh, sorry. Thank you. 5? All right. That's true. I didn't say whole numbers, but what was the number?
The number was 17.
So I think our closest was 15. So that was, did somebody say 18?
Who said 18?
You said All right. Well, I think 15 was our closest. So congratulations. You've won our first set of books. But there's more. Oh, sorry. Um, so this has even more books in it. This first one is called Our Threatened Planet. I think all the books in this bag are about planets. So there's the same deal here. I'm going to tell Doug the number so we know we're honest. All right.
Oh, you mean 5?
And so you have a hint now. Sorry? Is he double bluffing you? You never know. So who here would like a bag of books on planets? Same thing, think of a number between 0 and 20. Okay. All right, is that everybody? Oh, one more? Okay. I think 17 has not been taken. What was the number?
10.
So you were right on the money.
Last time you won a 12-inch telescope, this time that they happened.
Congratulations. This one is on. It is my first time. I specifically did this so I wouldn't have to play. So this last book is, I think, thematic for our talk today. It's all about black holes. So you guys are clearly here because you're interested in black holes at least a little bit. So would you be interested in a bag of books about black holes? I haven't selected the number yet. All right. Present your guesses. Yeah. Okay. And you, sir? Okay.
Eight.
You were right on the money. Great job. Thanks for having me be here.
Thank you very much, Laura. Well, Karen's got a mountain of books up there. Do we have any more for next month, Karen? Okay. Even one book? Okay. So stay tuned, come early, have fun, bring books home. Thank you. And thanks to Laura, her first club meeting.
Thank you. That hopefully has made Karen's life a little easier too, as our club librarian. Now, without further ado, I think it's time for the formal club announcements. And Kyle, I believe, is standing by to do them. So, Kyle?
Yep. I am here. All right, let me go from the start. There we go. All right. First off, welcome new members. Your name badges will be on the whiteboard there behind Barbara. If you're not attending the meetings in person, you can they'll be mailed to you in a couple months. Coffee, donuts, and water are upstairs by the library entrance. Those are available for purchase for $1 each. Star parties, the next ANSYS Star Party will be January 17th. Astrophysics will be, oh, that's the wrong, I believe there's January meeting, but that's not, I didn't catch that. The next beginners class will be February 6th. At Orange Coast College, and the next board meeting will be January 18th online. Here's how you find the information about the club's Adopt-a-Scope program. You can find the sample adoption agreement and sample inventory, along with more information about the program on our website. Martin Christensen is the outreach coordinator, and we have 2 outreach events coming up, one later in January and one in mid-March. If you're interested in helping with either of these fun opportunities to share the night sky with others, please reach out to Martin for more information about that.
Kyle, I think Martin wanted to say something.
Oh, yeah.
Probably, yeah. Keep it brief so we can keep it moving.
What I wanted to announce is that we have 2 more outreach events added to the schedule. One for February 27th at Cielo Vista Elementary School in Rancho Santa Margarita, and one on March 30th, the Cerritos Library Astronomy Night in Cerritos. So anybody who wants to come to those, there will be a moon out, of course, in those nights, because it's the end of the month, and that's the time, about the time the moon is full. So deep sky observing will be a little more difficult, but there probably will be plenty of planets. Great. Thanks, Martin. And if you want to volunteer for those, please get in touch with him. And those are always fun events. So back to you, Kyle.
Perfect. If you have Dave Fisher's the Serious Astronomer editor. If you have any items of interest that you think might be good to be featured in the club newsletter, such as articles, observations, trip reports, etc., please share those with him and he'll review those. Friendly reminder to all those who are using the ANSA site to lock the ANSA house, ensure all windows are closed, doors are closed, and that the gate to the site is closed as well if you're the last one to leave. Additionally, to help with fire prevention, please help keep your pad clear of weeds, and it would be much appreciated if you can help with weed clearance on all the public areas of the property. It's already mentioned that this is the final night to vote in the club leadership elections. You can either vote in person at the meeting if you're there, or you can send in your ballot electronically. You should have already received electronic voting instructions via email. If you didn't, I guess you could email John Hoop, but at this point it's probably a little late since voting closes in a couple hours. And here are the candidates. Again, even though these aren't competitive, elections, we do appreciate the support of you casting your ballot. The next general meeting will be February 13th. And I will turn it over to Chris Butler for the What's Up presentation.
Yes, and we seldom give Chris really an adequate introduction, but this is the gentleman from Griffith. He's had experience with planetarium shows on cruise ships. He's done a wide variety of things, and he has had a long history of doing great programs and What's Up events or presentations for our club. We are very, very happy that he is here tonight. Please welcome Chris Butler.
Yeah, big thank you. Big introduction, and then give him a mic that's been turned off. Thank you. That's wonderful. No, I can handle it. So for the What's Up, let's have a look at the sky. We'll see what in the world we can find. And one of these is the laser pointer thing, right? Is this the one? Yep. Okay, cool. Because there are actually things to point to this time. So let's jump in. First of all, the seasons have been changing. I'm finding I notice it a lot more now than I did when I was younger. I really, I don't get SADs. You know, it's not like I'm talking about jumping off a building. It's a good thing I work in a one-story building. But at the same time, I don't like it when it's really dark in that part of the year. And I like it when the sun starts to come back. You may be noticing already we are getting longer days. And in another week or so, it'll become much more noticeable to you. So a little more sunshine, that's okay, even for astronomers, but we have some very pretty winter stars to look at as well. We mentioned the moon phases, and yes, indeed, the very end of the month will have a kind of a 3/4 lit evening sky moon by the end of the month. So that'd be a good time for observing the moon. For those of you who want to see dark skies with the moon being absent, January 18th is the dark of the moon. Right now, at the hours I'm up, it may as well be dark of the moon because the moon's not coming up until midnight. And these days I have to get in bed before that. So last quarter moon, the half-lit moon that you see in the morning sky, that's on January 10th. Looking at the planets, it's kind of an interesting mix this month. We have some planets are really absent. Some of the famous ones are just not around, but others are very much around. Mercury is in the morning sky if you get up early. However, it's dropping like a stone. In fact, a stone about 3,000 miles across. It's dropping around back behind the sun very quickly. So you really would have a hard time catching Mercury right now. It will actually be back behind the sun on January 21st. And then you have to wait for it to come around in the evening sky. Not a very good time for Mercury. Terrible time for both Venus, brightest of all the planets, and famous Mars. They're both passing behind the sun. Mars, in fact, passing back behind the sun tonight. Hopefully it won't be too badly damaged by the excessive heating. Okay, just kidding. Sometimes we have college students in the audience. I like to freak them out. Jupiter is the reverse of what's going on with Venus and Mars. Jupiter is beautifully placed. I know a lot of you have just looked up and noticed its magnitude minus 2.7, whatever. It's brilliant in the evening sky. But I'll make the point that it is at its theoretical best right now. Jupiter is opposite the sun at opposition, so it's highest at midnight and all the rest of that. But it's even better than that because it's reaching opposition in Gemini, which is as far north or in our skies as high as major planets can ever be. So it's at opposition and it's passing as close to straight overhead as a planet can. So that's really a good time to have a look at Jupiter. Saturn, not so good. It's around if you want to hunt it down. You can see it with the visible eye over in the southwest-ish when the sky first gets dark. It's not that bright. You might notice that. Saturn can be quite a bit brighter than Saturn is right now. And I'll explain why in just a moment. But it is visible to the unaided eye. You can catch it with a telescope, but catch it quickly because it is all the way down when you get around to 10:20 p.m. So it sets pretty early. Uranus, beautifully placed. Lovely time for Uranus. It's in Taurus, the ball, not far from the Pleiades star cluster. So very good time to be looking at Uranus, which is my favorite planet if you're looking for trivia. It's the only one that's kind of green. I don't know why, but I like it. Neptune is over near Saturn. It's over in that part of the sky. While you could catch Saturn still, even if it's not at the highest, I wouldn't bother with Neptune because, of course, it's much fainter. You need darker sky conditions. You're really not going to get that with Neptune, even if right next door Saturn is okay. Pluto is also very low in the southwest. Sky pollution is going to interfere with this otherwise blindingly brilliant and huge object in your telescopes. So maybe give it a pass. I mentioned Jupiter was beautifully placed. This is a time where Jupiter is not only high and beautifully placed, it's also its equator is very closely lined up with us at the moment, so that you're getting lots of these neat shadow events and transit events with the satellites right now passing across the face of Jupiter. This includes the outermost of those moons, which is Callisto. It's a little bit more rare for the Callisto to cross the disk of Jupiter than the other moons. And the interesting thing about this, you'll notice I told you Jupiter is just opposite the sun right now. Look at Callisto and look where its shadow is. A lot of us have seen shadows cross on Jupiter where the moon comes first and then the shadow is much later. If there's any angle at all between which direction the sun is and that moon, the shadow will be way off to the side. But as Callisto will show tomorrow night, this is tomorrow night, about 1 o'clock our time, that shadow is right behind it. So you can tell you're looking straight away from the sun at Jupiter. So Jupiter's great. The moon's wonderful to look at. I mentioned with Saturn, the business with it not being as bright as sometimes it is. The reason for that, this is from theskylive.com. You can always check with this website to get a look at what's going on in the sky. Hey, they don't need me. I've been replaced. AI, wonderful. But you'll notice the rings are just about edge on. When the rings are just about edge on to us, they are reflecting much less light. When Saturn has the ring system tilted much more to us, and it can be tilted quite a bit more than this, you get a good look at the rings as a big fat oval. They put out much more light. And just looking with your eye, Saturn looks much brighter than it does tonight. But the edge on rings are really kind of spectacular, and that's what you'll see if you look tonight. Looking at the sky, just kind of a general view of the sky, right after the sky is getting dark, 6 p.m., it's going ahead getting dark. I looked and yeah, it looks just exactly like this. The names are a little bit fainter in the real sky. The lines are a little hard. Okay, no, nobody's buying this. All right, good, good. I'm glad. You've watched too many of these shows. I mentioned that Saturn and Neptune were over there, but we're setting pretty quickly. This is just as the sky is getting dark, and they're already proceeding over toward the sunset. You'll see in the next picture at 9 p.m., they really do head off of the horizon pretty quick. Uranus already well up and will be well up at, like when you get out of the meeting here, and Jupiter just starting to rise in the east. It'll be with you all night, and I mean all night. Looking at 9 p.m., kind of prime time for stargazing as far as I'm concerned. You can see Saturn and Neptune are well off towards the west. They're on their way down. Uranus is just, it's still in the very, very high part of the sky there. So Taurus and Uranus well placed for observation, and Jupiter is reigning supreme overhead. For theme, I will say what I'm going to be doing this evening for the star portion of the What's Up, the constellation parts. I'm actually going to be on an itinerary following from constellations way over here along the Milky Way. And I'm going to visit a number of these constellations. In fact, just about all of them along the path of the Milky Way. the many of the people here, you've never seen the Milky Way, right? I mean, if you've remained in the OC your whole life, you've dimly seen it. But don't worry, that's what earthquakes are for. A complete collapse of the power grid means all of you can run out, set up your telescopes, and by the flickering light of your burning neighbor's house, you can observe the stars. That's what being an astronomer is all about, knowing what's important. Anyway, this gives an impression of the sky at this time of night. You still have a shot at some of the fall constellations, but they're all on their way down by this point. And you certainly have a preview of coming attractions, things like the Big Dipper there in Ursa Major, the Great Bear, and Leo the Lion, and so forth. They're just starting to come up. Jupiter, by the way, I will say, is in Gemini, the twins, and you should probably note the presence of the two stars, Pollux and Castor, marking the heads of the Gemini twins. Jupiter is kind of like a third twin there, photobombing the other two. Looking at midnight, if you give it a little bit more time for the sky to rotate, read as the Earth rotating, you'll see Jupiter at its highest. Kind of amazing. Why is Jupiter highest at midnight? Because it is exactly opposite the sun. Right? The sun is at lower culmination, which is what we call it at midnight, when the sun is far underground and still exists. The earth is not flat. Just a detail, in case it comes up on a test. But you can see Jupiter is reigning supreme there. At midnight, the moon has just come up. It's actually more of a half-lit moon than I drew it here, but that's when you'll see it appear. 6 a.m., the sky is starting to get light. The moon would be at its highest at this time. And notice Jupiter is still with you, just as the light is starting to fade. Jupiter can be up for the entire night right now, meaning the minute it starts to get dark, it's up. When it starts to get light, it's up. It is totally up. It is the brightest object in the entire sky. If you can, apart from the sun and moon, if you cannot find Jupiter, we will actually kick you out of the club. So Jupiter is definitely something you want to look at. Looking at the Milky Way here, again, this is a view that is slightly darker, a light environment than Orange County. But this is the summer Milky Way. This is not where we're going to be talking about. In fact, this is the part of the heavens where the sun is right now, over in this area in Sagittarius. So you can't see that. But we're going to take off from the edges of the summer Milky Way in the northwest, go all the way across our sky like a giant rainbow bridge, and see the things that are visible along there. We'll start with Cepheus the King. Cepheus far in the northwest. This constellation has a lot in it. This is an example of something, the Cave Nebula. I admit I have not seen the Cave Nebula myself, but you could catch it this time of year. You need a dark sky, large telescope probably, but you could take images of it even from Orange County. Cassiopeia, the Queen, is one of my favorite ones. It's your next stop on your Milky Way road. Looks like a W or an M, depending on how it's rotated around the sky. It represents the throne of Queen Cassiopeia. The object that you see there, the Pac-Man Nebula in GC 281, is actually very, very easy to find in terms of where it is. This is something where you don't need computers to tell you, because in this pattern of bright stars you can recognize, it really is right there in the W pattern. If you just kind of memorize where it is, it's easy to put a telescope onto it pretty quickly, but you do need a dark sky. This is an example of one of the things we often don't hear about because it's a little bit fainter, the Heart Nebula, which is right next door to the Soul Nebula. This is a beautiful one. This is also in Cassiopeia. This is the California Nebula in the next constellation of, you can guess why maybe it was named the California Nebula. That's because they're trying to build a railroad from about here. No, I'm sorry. This nebula does bear an accidental visual relationship to the Golden State. It is not quite this bright or quite this colorful in most telescopes. Just saying, you may need to be prepared for a soft, faint, ghostly glow. Very pretty though. Here's an example of something you probably have not seen yourself before, Camelopardalis. Yes, of course, before the meeting, I was having a conversation with a friend, and of course, yes, we were talking about Camelopardalis, the giraffe, as one does. And the galaxies, though, we're talking about the galaxies that we all like in this constellation, including some beautiful nearby ones that are up in the areas of this away from the Milky Way plane. But I do want to make the point out that the giraffe constellation does dip its toes in the Milky Way. And in that area, there are some beautiful, often overlooked, but fainter, kind of ghostly things like the reflection nebula Vandenberg 15. Auriga is one of the famous bright constellations. It's where all military operations for the sky are operated in the Pentagon, of course. Just kidding, just kidding. But this five-sided shape up here, marked by nice bright stars, including Capella there, the only star that sings without musical accompaniment. Okay, the music majors, that was for you. You've been waiting years for that. There you go. Anyway, there are all kinds of beautiful things to see in through here. If you have a small telescope, there are a whole slew of star clusters in through here. But if you've got a telescope in a reasonably dark sky, the flaming star nebula that you see there is in the center of this bright pattern along the Milky Way in winter. Taurus the Ford is best known by the V-shaped. Yeah, I'm sorry, I got it. No one's going to even remember what a Taurus Ford is anymore. This V shape in here is the face of the bull, the star Aldebaran, which was, of course, blown up in 1977 in episode 4, A New Hope. Just kidding. No, this Aldebaran, not Alderaan. That marks the face of the bull. That marks his angry eye. He has two giant nuclear mutated long horns there. This supposedly looks like the body of a charging bull, with the Pleiades Seven Sisters star cluster being at his tail. However, we did mention Uranus is in this constellation. And this pair of stars kind of marking the back part of the bull. That's not a place you want to be, by the way. But if you go from the Pleiades about 1/3 that way down to those pair of stars, that's where Uranus is right now. Oh God, that's the right part of the bull for that to be, isn't it? I admit that didn't occur to me until just now. I beg your pardon. The only thing I want to say is some of these names here, I don't often hear used for some of these stars, but this one in particular really caught my eye. I don't know what language that is, but from now on, Omicron Tauri there will be known as Chunky Monkey. So I have no idea what that name means. It was mentioned on the previous chart, Heinz variable nebula, which is entirely made of ketchup, by the way. No, I never said that. But it's a nebula that seems to change shape as shadows are cast on it by dust passing near a star. The Spaghetti Nebula, Samis 147, is out near the horns of the bull. And it doesn't look like things are going too well for the people at Samis 147, but I wish them the very best. Here's a deep exposure photograph of Taurus showing that all parts of the sky really do have nebulosity and so forth, clouds of gas and dust floating in them. You can't see this kind of detail with your eyes normally. But Starbucks, you know, they offer all kinds of power drinks. You can try it and see how far you can go with this. But yeah, you can see all kinds of different things we were just talking about in there, like the Spaghetti Nebulas over there, the Pleiades star cluster. There's the California Nebula in there. Pretty remarkable photograph. Gemini the twins next door, as I mentioned. And this is about where Jupiter is right now, much brighter than these other objects. If you see something next to Jupiter, look over there and ask, what's that? Just the name of the star, sorry, Arabic name. Down in the feet of one of the twins, Castor twin, you will find the Jellyfish Nebula. Here's a general view of the winter sky here, showing some of the kinds of things we were just looking at. And of course, your eye is immediately drawn to the famous constellation of Orion with 3 stars for belt, 2 for shoulders, 2 for knees, and this situation hanging down below his belt. I ducked that very well, don't you think? That is, of course, the famous Orion Nebula. The much fainter Horsehead Nebula is also in this constellation. Orion is only a footnote mention here because I have been doing the What's Up since 1985, and I have had to talk about Orion every winter all those years. I'm so done with the Orion Nebula. It's like it gets all the press. It's on every magazine cover. Fine, there it is. I'm not angry about it or anything, no, I don't want to be on a magazine cover. But Monoceros the unicorn is right next door, and I do mean next door. There's Orion right there with that famous nebula. But there are some other beautiful nebulae right out in this part of the Milky Way. It's just kind of plain for there aren't many bright stars here. I've always said that this is proof that unicorns do not exist because there are no bright stars in Monoceros the unicorn. There are, however, the brightest of all stars in Canis Major, the great dog, including Sirius, which is a very serious star in the sense, no, it doesn't mean Sirius, our world, or our word. It means the sparkling one or the scorching one in Arabic. It is the brightest of all the true nighttime stars. Not quite as bright as Jupiter looks to us now, but of course, Jupiter is not a star. No matter what 2010 Odyssey said about it, it is not a star, and this one definitely truly is. For something exotic and unusual to find down here in the Milky Way, no, I'm not going to take you over to star cluster M41 like I always do. I'm taking you over to Thor's helmet, the middle of nowhere. This Thor helmet, no Chris Hemsworth in sight. This is a beautiful nebula that you can hunt down in that part of the sky. Last stop, the horizon's going to get in the way if we go any further, is Puppis the stern, the very back part of the great ship Argo Navis, barely comes up from Southern California at all. You've crossed the entire sky down towards the horizon in the southeast. You could barely get a glimpse here above the horizon of this beautiful nebula here, NGC 2467. It would be hard to observe so low in the sky. My main concern is if it looks like this, something has gone very wrong with your meds. It's time to call the advice nurse if it looks like that. So we have crossed all the way across the sky. We've seen brilliant Jupiter and, of course, Uranus in a very unfortunate part of the bowl. And we have crossed all the way over from Cepheus, all the rest of that, out past Taurus with the shape of the bull's face, the Seven Sisters, all the rest of that, past Orion, and then damn nebula. And then all the way down past Sirius and down into Puppis. That is enough to keep you busy. Absolutely. At least until I see you in a couple of months. In the meantime, thank you for your time and attention. I will now turn the microphone off before handing it to the next person.
Okay, well, thank you very much, Chris. As always, that was a lot of fun and also informative. Amazing. You actually get both in one package. Yes, but the best sort. It goes to show that we can do more than AI. Anyway, we are now at the point of greeting our main speaker for this evening, Adam Boesky. Sorry, I'm having problems reading here. Anyway, I guess I can't call him Dr. Boesky yet. He's on his way to being getting his doctorate, but he is in the PhD program at Harvard University and has been very much involved in a broad array of topics relating to astrophysical transients. Currently, he is going to be speaking to us about probably an ultimate transient type of event, black hole mergers. And rather than spending a lot of time on what I'm sure everybody has read on the website, I think I will just turn it over to Mr. Boesky, if he is here.
Hi. Yes, I am. Can you hear me all right?
Yes.
Hi, thanks so
Welcome.
much. Awesome. What a what's up presentation that was. Great combination of information and comedy. Wish I had that every day. So I guess I could present my slides here. Um, can you see? Do you see these all right?
Yes, we can see you. Thank you.
Yep.
Awesome. Yeah, so my name is Adam. Thank you so much for having me. It's a huge honor. Things like Orange County Astronomers are what got me interested in astrophysics and astronomy in the first place. So I think what you guys are doing is awesome. So a little bit, well, yeah. So my talk today is going to be about mergers of binary black holes and how they relate to gravitational waves. And hopefully by the end of the talk, you'll understand why I like to call them a cosmic tug of war. So let's start by just a little bit about me. I have a lot of sort of disparate interests in transient astrophysics. So I like large-scale surveys, gravitational waves, machine learning. Recently, I've had a growing interest in long-duration transients and an optimization company with some friends of mine in college, and I interned at SpaceX writing simulations of the Falcon rocket. So today I'm just going to be talking to you about gravitational waves and mergers. Also, if I cut out at any point, just let me know, and I can repeat myself. So just wanted to briefly shout out the amazing collaborators that I had for this project. So Flor Brookgarden, professor of astronomy at UCSD, was my mentor with the gravitational wave research I've been doing, and Ido Berger is currently my mentor at Harvard. They're awesome. So the story really starts here with gravitational waves. So this video here, which I hope ends up playing. Oh, maybe. Let's see. Maybe I could just play it here. Let's see. Yeah. So this video here is what gravitational waves look like. So gravitational waves are tiny, tiny ripples in the fabric of space-time that propagate through space and through matter, contracting and elongating space-time as they travel. Now, in reality, gravitational waves are much, much smaller than what you're seeing here. If this were realistic, it would be quite a problem. But gravitational waves distort spacetime by something like 0.1% the size of an atom. So they are extremely, extremely small. Um, Now, gravitational waves, or at least the ones that we are able to see in our universe, come from things like this. So, oh wow, this is another video. Let's see. So here we are looking at two black holes revolving around each other in what we call a binary black hole system. And as they revolve around each other, because they are extremely massive and pulling on each other extremely hard, they are emitting what we call gravitational radiation, which causes their orbit to get tighter and tighter and closer, and they speed up until ultimately they touch and they coalesce into one black hole, which is what we call a merger event. Could watch that one more time here. So in reality, gravitational waves happen from or are emitted from any matter moving throughout the universe. So me moving my hand around right now, or any of you guys moving, emits gravitational waves. It's just completely negligible compared to events like this because binary black hole mergers are so gravitationally energetic. So let's go back to presenter view. Sweet. So a large part of Well, now it works. So a large reason for why we actually care about gravitational waves is because nowadays we can detect these things. So for a little bit of history here, in 1916, the first prediction of gravitational waves was made by Albert Einstein. Now, gravitational waves are a result of his theory of general relativity. And way later, we decided to try to detect these things. Now, we detect them using devices called laser interferometers. Laser interferometers, one of which is shown in the top right here, that's LIGO, work. So the way that LIGO works is it has two tubes that form a right angle, and in that white building, they shoot lasers down the length of the tube at a big mirror at the end, and the laser reflects back and ultimately meets the other laser back at the building, and we see an interference pattern when the two lasers meet. Now, when a gravitational wave passes through the system, it it records a signature in that interference pattern. So what we see in the bottom right here is actually how we can see gravitational waves propagating through laser interferometers. So in the orange one in the top is LIGO's detection of the first gravitational wave at Hanford. So that's one of the laser interferometers that they have. And then the bottom is the detection at Livingston, which is the other one. So this was the first gravitational wave detection. This is GW 150914, and this was made in 2015. And that was at the time a huge deal. Nobel Prizes were won because of it, and it completely revolutionized astronomy. And today, actually, gravitational wave detections are pretty common. So at this point, recently we just passed the 200 detection mark from LIGO, Virgo, and Kagra. So we're kind of actually gaining a pretty big catalog of gravitational waves at this point. And so after gravitational waves were detected, a few subfields of gravitational wave astronomy came out. So they're splintered off because of it. So a few of these are listed here. Testing GR is basically comparing the waveforms that we see from gravitational waves to what general relativity actually tells us should exist. And that way we can see the accuracy uh, of general relativity and Einstein's initial equations. Multi-messenger astronomy is using both light, gravitational waves, gamma ray bursts, or sorry, gamma rays, and different types of messages to probe astrophysical objects and events, and use like sort of a multi-pronged approach to look at sources in the sky. Gravitational wave cosmology is a really interesting field, in my opinion. I think something that's really cool about gravitational waves is that the strength of gravitational waves falls off as 1 over the distance to the source, whereas the strength of light falls off as 1 over the distance squared. So that means we'll actually be able to see much farther with gravitational waves than light, which means that it'll be easier to look at the early universe using gravitational waves. So that's kind of a really exciting subfield. Instrumentation is obvious. I think anyone trying to detect something that's 0.1% the size of an atom probably is going to revolutionize how we do engineering and whatnot. And then the field that I am a part of is gravitational wave paleontology. So that's this last one here. Um, the way that gravitational wave paleontology works can roughly be thought of like this. So this is what leads up to and creates gravitational waves. So on the left here, we have a binary star system. Now, this binary star system evolves. It might undergo mass transfer. The stars might interact in some way. They might have a common envelope event. And eventually, some of them will turn into binary black holes, which is what's in the middle. So that's those two black holes that we saw revolving around each other a few slides ago. And what we know about these is that they'll emit gravitational radiation, ultimately getting close and undergoing a merger that emits a gravitational wave. So this is sort of the storyboard of the lifetime of a binary star that produces the gravitational waves we see. So in the same way that paleontologists use fossils to understand the lives of dinosaurs, we use the remnants of binaries, the gravitational waves, to understand the lives of the stars. And so the stars and the black holes. And in doing so, we can answer questions like, how did the binary form? Did the stars ever interact throughout their lifetimes? How did the stars turn into black holes? And many, many more questions. Now, the way that I actually do gravitational wave paleontology is through a method called population synthesis. Population synthesis is a forward modeling technique. So we begin by drawing uh, drawing sampling from initial distributions of properties that we believe to be representative of the universe, and sampling to create sort of a zero-age main sequence binary, or basically just a very young, out-of-the-box vanilla binary star system. And then we take this star system and we evolve it parametrically according to observations that we've seen about how stars evolve. The software that I use to parametrically evolve binaries is called Compass. Something that's really nice about this is that Compass is extremely fast and computationally cheap, so we can actually evolve large populations of these stars at the same time in order to get a population analysis of what's going on with our gravitational wave events. And so when you evolve these, we evolve them to the end of their lives, and the end of their lives could look very different. So they could merge as stars. One of them could undergo a supernova and turn into a nebula. They could actually fall out of orbit with one another, but a small fraction of them actually result in a binary black hole that ends up merging. And so that's the population of them that we actually care the most about, obviously. And with these binary black hole mergers, the ones that actually create these gravitational wave events, we get some results that look something like what we have in the bottom right. So this is sort of like a storyboard of their lifetime. So we see what happened from the birth of this binary to the death of this binary, and we can use those results to understand what happened to the gravitational wave events that we actually observe in the universe. And so the metric that I am personally most interested in is the merger rate. So the merger rate is defined as the number of mergers per year per volume of the universe. And the rate provides insight into a lot of interesting astronomy and physics. We can probe black hole physics. We can begin to understand the events that led up to the merger of a binary. We can actually probe the demographics of the progenitors of a binary black hole system. Unfortunately, however, the merge rate is super poorly constrained. So in this figure in the top right here, we're looking at the local merger rate density. So that's the merger rate at a redshift of 0. That's just in our local universe. And each of those horizontal lines are different papers' estimates of what the merger rate actually is. As you can see, the estimates of the merger rate span 4 to 5 orders of magnitude. So basically, they are completely uninformed, and we don't have any understanding of what the local merger rate really is. Luckily, however, the population of our gravitational wave events that we have seen is rapidly increasing. So, as I said, we recently passed the 200 mark, and we are going to be detecting way more in the coming years due to new detectors coming online. And beyond that, next generation detectors, which I'll touch on a little bit later in this talk, like the Einstein telescope or Cosmic Explorer, are going to be able to detect gravitational waves that come from very high redshift, very far away, beyond a redshift of 10. So not only are we going to be able to observe the events or the merger rate at this green circle in the bottom right here, but we're going to be measuring that whole curve, the merger rate as a function of redshift, which is really exciting. And so I'm interested in the redshift evolution of the merger rate, what the shape of that curve in the bottom right actually looks like. And in the literature, studies typically claim that the merger rate just follows the star formation rate density. So the star formation rate density is the number of stars formed per year per volume in the universe. And this claim makes a lot of sense. So as we just learned, binary stars turn into black holes, which end up merging and producing these gravitational wave events. So the more stars you have, the more mergers you should have in theory. Now, a lot of people use models of the merge rate to do studies to do like studies on that probe things like or that give estimates of things like how many mergers we'll detect with future detectors, or even try to measure the star formation rate using a model of the merger rate. So in order to actually get a model of the merger rate, people take the star formation rate and they add some delay that is supposed to account for the duration between the formation of the binary and its actual merger, because that can take a while. From one of the LIGO papers. In blue, we have the merger rate estimated from the catalog of gravitational waves that we have detected. And in black, they are plotting over it the star formation rate. And so this claim that the merger rate just follows the star formation rate looks somewhat fair. This is only between a redshift of 0 and 1.5. So we don't really know how it behaves beyond 1.5 at this point. And the error bars on the gravitational wave inferred merger rate are pretty big. So my question was for this study, well, is this true and does it hold for higher redshifts? So the way that I calculate the merger rate using population synthesis looks like this. The details of this are quite complicated, but hopefully I can just synthesize them simply here for you. So the way that I calculate the merge rate is I use population synthesis to evolve a huge number of sample binaries. And then I take these binaries that actually form gravitational waves and I integrate them throughout a metallicity-specific star formation history. Now, that details of that aren't really important, but basically you do some probability and integration to understand how these binaries would exist at different stages of the universe, like throughout redshift. When you do that, the output is a merger rate, kind of like this in the bottom left. So that's the number of mergers as a function of redshift. And something that I didn't mention yet, but is very important, is that in population synthesis, we have to assume a model for binary evolution in order to actually parametrically evolve these stellar binaries. And these models are fairly uncertain. So in order to account for this uncertainty, I varied a few parameters in order to see how the merger rate changes with different models for binary evolution. So this figure here is kind of the crux of my results. Each of these different colored and styled lines represents the merger rate that we calculated and simulated as a function of redshift. So each of the different colors are different models of binary evolution. And that's not super important, but it just accounts for uncertainties in our models, basically. And the black line that we're plotting over it is the star formation rate scaled. And so the question that we had is, does the shape of that black line align with the shape of those colored lines? And you can already tell that it kind of doesn't. So if you look at those green and orange models, the peak is a little bit lower redshift than the peak at about 2 for the star formation rate. And there are also some features in a lot of these, like a bump in one of those purple models at a low redshift, and they also fall off at high redshift, more so than the star formation rate. So in order to do a quantitative comparison of that black line to those colored lines, we simply took the colored lines and divided them by the black line. And if you divide anything by itself, it should just be 1. So if those things did follow the shape of the black line, they would just be this gray horizontal line at 10 to the 0 or at 1. What we find is that they are actually not. Uh, they are at low redshifts, they deviate by a factor of up to 4. They're way above that gray line. And then at high redshifts, they deviate by a factor of something like 0.5. So they're way below that gray line. And so we concluded that the merger rate does not follow the star formation rate perfectly. And the question then becomes, what causes this deviation? Why does the merger rate actually deviate from the star formation rate? And so today, I'm hopefully going to convince you that the two reasons are metallicity and delay times. Metallicity pulling to higher redshifts to the right, and delay times pulling to lower redshifts to the left. And hopefully that'll make sense. But first, for a little background on metallicity. So metallicity is defined as the proportion of elements in the universe that are heavier than helium. Astronomers actually call anything heavier than helium a metal, which I think is pretty hilarious. But metals in astronomy are created by enrichment. Now, early in the universe, everything was comprised of just hydrogen and helium. And as stars burn their fuel and undergo supernovae, they create heavier and heavier elements and deposit those elements back into the universe. This process is called enrichment, and it results in the amount of metals in the universe increasing over time. So in this plot on the right here, they are showing the metallicity in that black line as a function of redshift or the age of the universe. And we see that metallicity is increasing steadily as time goes on in the universe, which makes a lot of sense. And a known effect of metallicity on binary black holes is that metallicity decreases the formation efficiency of binary black holes. So what that means is if you have a binary star system that is highly metallic, we are unlikely to actually create binary black holes from that system. So the reason for this is, well, there are a lot of reasons, but the biggest one is because metals cause stellar winds, which drive mass loss. So those winds sort of strip mass off of the star. And mass loss results in two key things. First of all, it makes the star lighter, obviously. And if we want to get a black hole out of a star, it needs to be heavy. It needs to retain that mass so that it turns into a black hole, as opposed to something like a neutron star or a white dwarf when it undergoes a supernova. Mass loss is also bad for getting binaries to get closer and closer together because it decreases the amount of angular momentum in a binary. So as we just learned, high redshift has low metallicity, which means that binary black holes are going, or the formation of binary black holes is going to be favored at high redshift. So in this plot here, we're showing the formation efficiency of binary black holes as a function of redshift in that same comparison style to the star formation rate like we did a few slides ago. And what we're seeing is that the formation efficiency the number of binary black holes formed for all of our models favors high redshift significantly and in a very similar fashion for every model. So the formation efficiency of these binaries is boosted at high redshift. To drive that point home, here we are showing the formation efficiency of binary black holes as a function of metallicity. And what we see is that there's an order of magnitude decrease in formation efficiency around a metallicity that's half of what our sun is. So that means for the same amount of mass seated at high metallicity and low metallicity, we are going to be way more likely to form a binary black hole out of that mass if it is low metallicity. So metals plus stars do not equal black holes and therefore do not equal gravitational waves. And so this is sort of the beginning of the tug of war, or one of the opponents in the tug of war that I talk about. This is taking the merger rate and pulling it towards high redshift, or boost because it's boosting the formation efficiency of these binary black holes at high redshift. Now, the other opponent is delay. So, delay times, delay when it merges as black holes. So it's sort of
We just lost you for a couple seconds.
Oh, sorry, where was I?
It was just before you went to the current slide.
Gotcha. Okay. Well, yeah. So I was just talking about how metallicity is boosting our formation efficiency, pulling the merger rate to high redshifts. Now, the other opponent is going to be the delay times. So delay times are defined as the duration between the formation of a stellar binary and its merger as black holes. So it's sort of the time difference between the leftmost stage and the rightmost stage in that image in the bottom right. So these durations vary a lot. They can be anything from a few million years all the way until Hubble time, which is the age of the universe. Um, in the figure on the right here, we're taking one model and plotting its delay time distribution as uh, at a few different redshifts in those different colors. And what we see is the delay times actually are changing as a function of redshift, which is kind of a novel finding. It's not something that anyone has ever realized before. And also, typically in the literature, people claim that the delay time distribution just follows that power law dash line, that 1 over t distribution. And we're finding that it doesn't really, it actually tails off a little bit more at lower delay times. But regardless, the big idea here is that delay times cause binaries to actually travel to lower redshift before merging. So hopefully this video here will explain why that is. So stars are formed at a low redshift, then it takes some time for them to actually evolve. So they form at low redshift, they end up turning into a binary black hole, and then they spiral in, spiral in, spiral in, and take some time to actually uh, spiral in and collide and emit that gravitational wave at some lower redshift. Great. Um, and so, as I mentioned before, the delay time distribution seems to change as a function of redshift. So in the figure on the right here, I'm taking the median delay times for each of the models that we simulated, and I am plotting it as a function of redshift. And what we see is the median delay time not only varies model to model, but it also changes as a function of redshift. And it changes in different ways model to model. So it's already pretty hard to wrap our minds around how delay times cause binaries to travel throughout Redshift. So it's going to be even harder if the duration of the delay time changes as a function of Redshift. So basically, there are going to be really non-trivial effects of this process on the merger rate. This implies that delay times are a significant source of model to model merger rate variation, because the duration changes model to model. So the actual shape of the merge rate is going to be really different. So all in all, this is the other opponent that I was describing, and this is the cosmic tug of war. So metallicity boosts the formation efficiency at high redshifts, causing the merge rate to be favored at high redshift. And then delay times cause these binaries formed at high redshift to travel to low redshift before actually merging, where we observe them. So that's the tug of war. And as I said, a lot of times in the literature, people will use the merger rate to do studies about other things. And they use a model of the merger rate that is the star formation rate delayed. So here, what I'm doing is comparing different models for the merger rate that people use in the literature to our simulated merger rates. So in the top, we have the star formation rate convolved or combined with a constant merge rate of 20, or sorry, with a constant delay of 20 million years. And then the bottom, it's convolved or combined with a delay that follows a 1 over t distribution. So in the top, what we're seeing is that the constant delay fails to account for mergers at a redshift less than 2 that come from high delay time, from the high delay time tail of the delay time distribution. So there's some binaries that are going to take a really long time to merge. And so those ones are going to merge at low redshift. So this constant delay fails to account for that. And for the power law or the 1 over t distribution, it's just overlooking the favoring of higher binary black hole formation at high redshift as a result of metallicity. So both of these are pretty bad models for the merger rate as we have simulated. Also, something that's kind of interesting is that in the literature, a lot of people claim that the power law distribution is pretty similar to a constant distribution because power laws are so sharp. As we can see from the difference in the looks of these two rows of figures, that is clearly not true. There's a pretty big difference between the two impacts of the delay times. And so another technique that is used often in the literature is to get a model for the merge rate is people will take the star formation rate and scale it so that the local merge rate in the model matches the merge rate inferred by gravitational waves. And so in this figure here on the left, what we're doing is we're taking the merge rate and we're taking a star formation rate that is scaled so that it matches the merge rate at a redshift of 0. And we're doing that division to see how the shapes align. And what we see is there's a really, really drastic misestimation in how these star formation rate based models for the merge rate uh, actually compare to the merge rate. In the middle, we have that constant delay version of the star formation rate. And in the right, we're doing a power law distribution for the delay time as well. So what we're seeing is there's drastic, like order of magnitude misestimations beyond a redshift of 1. And this is really bad because future detectors, studies often will use these models to approximate how many mergers they will be seeing when they start looking at higher and higher redshifts. And so that means that their estimates for the number of mergers we might be seeing are going to be really off. And so here's sort of a conclusion slide of that study. So all in all, the merger rate redshift evolution is really different from the star formation rate density by a factor of up to 4 times. This results in studies probably severely misestimating the number of mergers that they are actually that they will actually be detecting. Second, the reason for this is that there's kind of a tug of war going on. So metallicity is causing uh, a favoring of high redshift uh, formation in binary black holes, and delay times cause these binaries to go to lower redshift before actually merging. And then finally, kind of a neat little fact is that the delay time distribution is redshift dependent and varies by model, which is one of the just another novel finding here. Um, and uh, I think what's really exciting is what's next in gravitational wave astronomy. So the next thing that I'm excited about personally is LISA. So LISA is shown in like an artist rendition in the top right here. LISA is going to be a space-based detector, the first detector that we put in space. It's supposed to launch in 2035, and it's going to be this triangle formation of these objects shooting lasers at each other, and those arms of the triangle are going to be 2.5 million kilometers long. So that's kind of crazy to think about. And it means that we're going to be sensitive to a whole new mass regime of black holes. So supermassive black holes interacting with objects emit longer wavelength gravitational waves, which are not able to be picked up by our relatively short detectors right now. But when we have 2.5 million kilometer uh, laser distances, that's going to be able to actually pick up on supermassive black hole emitted gravitational waves. Now, the other two next generation detectors coming up are Einstein Telescope and Cosmic Explorer. These are going to be ground-based detectors that are just going to be way, way more sensitive. Um, so sensitive that they're going to basically be observing the very first moments of the universe, which is super exciting for us. And in the bottom right here, I think this puts things into nice context. The y-axis is the number of detections that humanity has made, and the x-axis is time. So we're at 2026. We have about 200 detections right now. And by 2035, we'll have several thousand binary black hole detections. With Cosmic Explorer and the Einstein telescope, by 2040, we'll have hundreds of thousands to maybe millions of detections, which is going to put us in sort of a big data paradigm for gravitational wave astronomy. So, yeah, that's sort of what's coming up next with gravitational wave astronomy. Um, and yeah, that was my talk. So thank you guys so much for listening. I guess we're going to do some questions, so I'll leave this conclusion slide up for you guys to look at.
Thank you very much. I hope you can hear the applause in the auditorium. I don't know
I
how much
can
of that
see
the
it.
microphone could pick up, but then we also have people online that are showing their appreciation otherwise. I have just one basic question. Have any of the models that you talked about been checked against the data that you already have, the 200 observations?
Hmm. Uh, yeah, so for the purposes of my study, not so much. The thing is, the observations that we have today don't extend to high redshift, which means that the redshift evolution is going to be, or like our merger rates go out to way higher redshifts, the simulated ones. So we have compared the local or the redshift zero merger rate to what we have inferred from the gravitational wave catalog, but it's not going to be super informative beyond a redshift of zero.
Well, 200 sounds like a good number, but I realize that's just the beginning. So just checking the auditorium first, do we have any questions? Yes, sir.
Sorry, I'm not hearing anything. If you guys are speaking.
Well, the initial comment was that John is impressed by the and he put in the comment that one of his colleagues keeps talking about having more data, which I think we all would like. Going on?
Yes.
Hey, John, why don't you come up and ask your question directly? Because I think that'll be easier than me trying to translate.
I was curious what methodology you used in mathematically generating your initial seeds for the populations that you were growing. Were you using something like a Monte Carlo method to generate your initial parameters?
Yeah, exactly. So we have these distributions that we believe to be representative of the properties of stars in the universe that we have fitted to data. And we just take those distributions and we sample them, basically.
Given that that's your methodology, should quantum computing ever actually come to fruition, how would it influence your ability to investigate this statistically?
Yeah, that's a good question. So, for our purposes, population synthesis simulations are relatively computationally cheap. So, actually doing the simulations takes something like a few seconds per binary, evolving them from birth to death. Um, so, we I don't think that I don't think that quantum computing is going to directly help us so much in the field of population synthesis, but I do know that higher fidelity models for evolution will be way more computationally expensive. So using quantum computing for those might benefit a lot.
Thanks. Yes, Tim?
Sorry, I'm not hearing anything. But
Um, I believe that the question is early in the talk you spoke about binaries being generated, and the question is there something about binary stars in that, because they're binaries, makes it more likely that they would become black holes and then subject to merger?
Gotcha. Interesting. So, yeah, that's a good question. It's a little bit of a complicated answer. So gravitational wave events and mergers are there are a few different ways that people believe they might actually come about. So in our case, we're thinking about binaries just as isolated stars and black holes revolving around each other. But there's probably some mergers that come from more dynamic environments. So something like at the center of galaxies where there are a lot of bodies interacting gravitationally with the black holes at play. And yeah, so towards that end, those instances, like in our case, we're studying just the isolated uh, paradigm, but there are sort of other ways that these gravitational waves might be emitted that some people have theorized before.
The question is, you had mentioned that there would be more ground-based detectors coming online. And the question is, what is the difference in the technology that you expect is going to result in such a greater detection rate?
Yeah, that's a great question. So, the difference in the technology is that some of these detectors are going to be placed underground, which helps us avoid seismic activity. So, we're trying to detect things that are extremely small. So, a bird chirping or a car driving by these detectors might actually register as something like a gravitational wave, or will be noisy enough that it'll be difficult to differentiate. So we are putting things underground to get to sort of help avoid that seismic activity. And also, the arms of these detectors are going to be significantly larger and longer, which is going to allow for higher sensitivity. There's also a ton of different engineering innovations that honestly I'm not an expert in at all. But yeah, there's those are the two biggest reasons that those are better.
Great. Let me hand this over to Alan for some online questions.
Okay, the first question is how delay times between black BH to BH, BH to NS, and NS to NS mergers? Yeah, how do
Yeah,
the delay
that's a
times
great
vary?
question. Yeah, that's a great question. So, they do vary a lot. I would say the black hole neutron star merger delay times, the distributions, um, vary as having more variable evolution. Um,
Can you go over that again? We lost you briefly.
oh yeah, sorry. So I was gonna say, it's a good question. So black hole neutron stars and neutron star binaries uh, are their delay time distributions vary more model to model as a result of neutron stars having more variable evolution. So the answer to that's a little bit hard because our models for evolution are uncertain and end up dominating the actual results in the delay times. I do have kind of a paper to this. If you just look up my name, there will be a paper that goes through the delay time results comparing these three cases. But yeah.
Okay, thank you. There's another question. How do two black holes form in a binary system without their precursor stars cannibalizing one another or merging prematurely?
Yeah, so that's a really, really good question. So it's basically it's very, very hard to take a binary and end up with a gravitational wave. Um, as we said, well, let's see if I could go to the slide. Um, in this slide, as I mentioned, we have to seed several million zero-age main sequence binaries in order to get a population of probably a few hundred or 1,000 binary black hole mergers. So they're extremely rare because a lot of them will get disrupted or end in different deaths. So to the short answer is it's really hard. The longer answer is uh, when stars are in orbit, they're typically far enough away that a supernova will oftentimes not actually end up causing a detachment in their orbit. So if one star undergoes a supernova, it won't necessarily mean that the orbit gets completely disrupted because there's enough distance between the stars. But yeah, there's a lot of dynamics going on there, and it's kind of an area of active investigation of how do we actually get these merger events from just normal binary stars.
Any other questions in the auditorium? Well, I think that's all the questions we have, and that's all the questions we have online.
Sweet.
Thank you very
Well,
much for your talk. It was very interesting.
yeah, thank you guys so much for having me. Appreciate you taking the time to listen.
Yeah, we really appreciate you coming and look forward to seeing what additional research you're going to be doing in the future.
Thank you.
Take care. Bye-bye. And there's more applause coming your way.
Thanks.
Okay, so with that, I think that's the end of the January meeting. Again, get your votes in if you haven't so far today, and or whatever. And thanks again to our wonderful speaker, and we'll see you all next month.